Tonight, we're going to talk about something that is sitting, right now, roughly 1,700 kilometers beneath the red dust of Mars. Something that, according to almost everything planetary scientists believed a few short years ago, simply should not still exist. Picture a wine glass dropped onto a tiled floor. It doesn't crack neatly in two. It shatters, a few large shards, and then a spray of countless smaller fragments, scattered outward in a pattern that looks chaotic but actually follows a precise, repeatable mathematical rule. Now imagine that exact same shattering pattern, at the exact same mathematical proportions, frozen in place, buried deep inside an entire planet for 4.5 billion years. That is almost exactly what a team of scientists announced they had found in August 2025, hidden inside the mantle of Mars. Not smooth, layered rock, the way every rocky planet's interior is generally assumed to settle into, given enough time. Something closer to rubble. Kilometer-sized chunks of ancient, compositionally distinct material scattered through the deep interior of an entire world, apparently untouched, apparently unmixed, apparently exactly as violent and as chaotic as the day they were created, during the first 100 million years of the solar system's entire existence. Here's what most people don't realize. We didn't find this by drilling. Nobody has ever drilled anywhere close to a planet's mantle, on Mars or anywhere else. The deepest hole humanity has ever cut into solid rock, anywhere, reaches barely 0.2% of the way to our own planet's center. We found this by listening. A single French-built instrument, sensitive enough to detect ground movement smaller than the width of a single hydrogen atom, sitting alone on a flat red plain for 4 years, recording the faint tremors of a planet quietly settling its own bones, and in doing so, accidentally photographing, in sound rather than light, the actual moment of Mars' own violent birth, still preserved, still sitting there, 4,500 million years later. The first surprise is just how genuinely impossible it is to see inside any planet at all, including our own, and exactly how far humanity's best drilling technology has ever actually managed to reach. The second surprise is the specific, almost accidental way we finally solved that problem, not with a drill, but with an instrument built to listen to a planet shake. The third surprise is what that listening actually revealed, layer by layer, about a world that turns out to be stranger and more surprising than nearly every model predicted. A molten layer nobody expected, a core built from an entirely unexpected chemistry, and, right at the center of tonight's story, chunks of debris that should have been erased by now and simply weren't. And the fourth surprise is what all of this tells us about why Mars died, and Earth didn't. A story that reaches far beyond one red planet into the deep interior of every rocky world we will ever hope to understand anywhere in the galaxy. By the end of tonight, you're going to understand exactly how a small, silent robot, sitting motionless on a Martian plain for 4 years, ended up rewriting the story of how rocky planets are born, and why the fragments it detected, buried deep inside Mars, shouldn't, by any reasonable expectation, still be there at all. Before we dive in, if you're someone who finds real comfort in this kind of patient, honest exploration of the universe, who trades the noise of the day for a little cosmic perspective before sleep, consider liking this video or subscribing to the channel. It's a small thing, but it helps us keep making this kind of content for people who share that same quiet curiosity. Now, let's begin. Let's start with a rusted steel cap, bolted shut over a hole in the frozen ground of the Kola Peninsula in the far northwest of Russia, near the border with Norway. It sits there today, largely forgotten, in a landscape of scattered birch trees and abandoned scientific buildings, and it represents, without any serious competition, the single deepest wound humanity has ever deliberately cut into the solid body of our own planet. Between 1970 and 1992, over the course of more than 2 decades of continuous, obsessive effort, Soviet engineers drilled what came to be known as the Kola Superdeep Borehole. A single narrow well sunk straight down into the continental crust in pursuit of one goal: to see, directly, physically, with actual retrieved rock in hand, how deep humanity could actually go. It was, in its own way, one of the most ambitious scientific undertakings the Soviet Union ever attempted outside of its space program. A decision made at the highest levels of Soviet science policy that understanding the deep Earth mattered enough to justify decades of sustained national effort. The well, designated SG3, reached its final depth in 1989, 12,262 meters, 12 kilometers and change, straight down into solid crystalline rock. Say that number slowly, and it sounds genuinely impressive. Deeper than Mount Everest is tall if you flipped the mountain upside down and buried it in the ground. And it is impressive as a feat of sustained engineering. But now, compare it to the actual scale of the planet it was drilled into. Earth's radius, center to surface, is 6,371 kilometers. 12 kilometers against 6,371 works out to a genuinely humbling fraction, roughly 0.19% of the way to the center of our own planet. Not 2%, not even 1%, less than 1/5 of 1%. The absolute technological limit of what human beings, using every tool at their disposal across more than 2 decades of dedicated effort, have ever managed to physically achieve. And it wasn't ambition that stopped the drilling. It was the rock itself, refusing to cooperate. Engineers working on the project's 4th deviation borehole had modelled, in advance, what temperatures they should expect to encounter as they descended. Predictions based on the best available understanding of how heat flows outward from Earth's own interior. At 11,882 meters, the actual measured temperature reached 180 degrees Celsius, dramatically hotter than the roughly 100 degrees the models had predicted. At that temperature, the crystalline basement rock stopped behaving like solid stone at all and began behaving instead like something closer to warm plastic, flowing slowly but relentlessly back into the borehole faster than the drilling equipment could clear it away. The hole was, quite literally, healing itself shut from the bottom up faster than anyone could dig. Drilling stopped in 1992. Not because the scientists ran out of curiosity, because the planet itself, at a depth that still represented less than 1/5 of 1% of the journey to its own center, physically refused to let them go any further. What the Kola well did find in that comparatively shallow slice of crust genuinely surprised the geologists involved. They found free-flowing water 6 kilometers down in rock that every existing theory said should have been bone dry at that depth, apparently squeezed directly out of the surrounding mineral structure by the sheer, immense pressure of everything above it. They found microscopic fossils, roughly 2 billion years old, preserved in the ancient crystalline basement rock. Direct physical evidence of life that had existed on Earth for an almost unimaginable span of time before anything resembling a human being ever walked the surface above it. They found a temperature gradient below about 7 kilometers, considerably steeper than anyone had modeled in advance, forcing an entire generation of continental heat flow calculations to be revised. And they found, at the specific depth where Soviet seismic models had confidently predicted a transition from granite to basalt, no transition at all. The expected boundary simply wasn't there, exactly where decades of remote seismic prediction had said it would be. To actually reach Earth's mantle by drilling straight down from a typical continental surface would require boring somewhere between 30 and 60 kilometers of hole, roughly 3 to 5 times deeper than Kola ever managed, through rock that, based on what Kola already revealed, becomes progressively less cooperative, not more, the deeper you go. It has never been done. With the drilling materials and techniques available to us today, it very likely never will be. There is exactly one place on the entire surface of our own planet where humanity has ever come genuinely close to directly touching actual mantle rock, and it required an entirely different strategy altogether. Not drilling down through thick continental crust at all, but finding a spot in the deep ocean where the mantle itself had already been tectonically shoved upward, close enough to the seafloor that a considerably thinner layer of crust stood in the way. In the spring of 2023, an international drilling expedition aboard the research vessel JOIDES Resolution targeted exactly such a location. The Atlantis Massif, an underwater mountain rising from the mid-Atlantic ridge, near a remarkable formation called the Lost City Hydrothermal Field. Drilling through more than 700 meters of open ocean water, and then continuing down into the seafloor itself, the international research team penetrated a single borehole to a total depth of 1,267.8 meters below the ocean floor, recovering more than 71% of the rock they cut along the way, an extraordinary success rate for this kind of deep ocean drilling. That single core, 1.2 kilometers of continuously recovered mantle-derived rock called peridotite, represents the deepest, most complete, most direct sample of Earth's own mantle that human beings currently possess. It is a genuinely monumental scientific achievement, the product of decades of institutional expertise and enormous logistical effort. And it is, in the story we're about to walk through tonight, a rounding error. A fraction, smaller than a fraction, compared to what a single, silent seismometer, sitting motionless on the surface of an entirely different planet, was able to reveal about that planet's interior from a distance of over 1,500 kilometers without ever touching a single grain of the rock it was actually studying. Before we follow that seismometer to Mars, it's worth understanding exactly what a planet's interior is generally expected to look like, because Earth, our only fully mapped example, gives us the baseline against which everything about Mars would eventually turn out to be surprising. We have mapped the surface of Mars to a resolution finer than a single meter. The HiRISE camera aboard NASA's Mars Reconnaissance Orbiter can resolve individual boulders scattered across the Martian surface from orbit. We have driven wheeled rovers directly across ancient, dried-up river deltas. We have, remarkably, flown an actual helicopter through the thin Martian air. And yet, until a specific date in late November 2018, humanity knew less about what existed 500 kilometers beneath the Martian crust than a medieval European geographer knew about the far side of the Pacific Ocean. The problem, at its core, isn't really one of insufficient effort or insufficient cleverness. It's a fundamental limitation baked into the physics of how we're able to observe anything at all across any distance. Telescopes detect photons, particles of light, which simply cannot pass through solid rock in any useful way. Orbiting spacecraft see surfaces and surfaces alone. Landers, at best, scratch and sample the uppermost centimeters of soil directly beneath them. None of these approaches, however sophisticated, can actually look through solid rock to see what lies beneath it. Radar can penetrate a modest distance, a few tens of meters, at best, under favorable conditions. Gravity measurements, taken from orbit, can reveal the aggregate density of a planet's interior, layer averaged against layer, but cannot resolve any real internal structure. They tell you how much mass is down there, in total, without telling you how that mass is actually arranged. To genuinely see inside a planet, to resolve real structure, real boundaries, real layers, you need something capable of physically passing straight through solid rock and being recorded again on the other side. There is exactly one such tool available to modern science: seismic waves. Earth remains our only complete tutorial for what a fully mapped planetary interior actually looks like, built from more than a century of dedicated terrestrial seismology. By now, the layered structure is known with a precision that would have genuinely astonished the field's earliest pioneers. A crust ranging from just 5 kilometers thick beneath the deep ocean floor to as much as 70 kilometers thick beneath the tallest continental mountain ranges. A thin, brittle skin of granite and basalt wrapped around everything beneath it. Below that, a mantle roughly 2,900 kilometers thick, made of dense, semi-solid silicate rock, rich in iron and magnesium, its temperature climbing from around 1000 degrees Celsius near its uppermost boundary to nearly 4000 degrees at its base. Beneath the mantle, an outer core, approximately 2,200 kilometers thick, composed of molten iron-nickel alloy, at temperatures ranging from 4,000 to 6,000 degrees Celsius. And at the very center, an inner core with a radius of roughly 1,220 kilometers, solid iron-nickel despite temperatures approaching 6,000 degrees. Hotter at that depth than the visible surface of the sun itself, held solid not by coolness, but by the sheer, crushing pressure of the entire planet pressing down from every direction at once. This entire layered architecture rests on a single, elegant fact, only fully decoded during the 20th century. Earth is layered because it once melted completely, early in its history, and its heaviest elements, principally iron, sank downward toward the center, while its lighter elements rose toward the surface. Scientists call this process differentiation, and it is universal. Every rocky planet in our solar system went through some version of it, in the earliest, most violent chapter of its own formation. But Earth remains, as far as we currently know, the only rocky planet where the mantle has continued convecting, churning, slowly but continuously, like an unimaginably slow pot of boiling water, vigorously enough and for long enough to have thoroughly erased almost every trace of that initial chaotic formation period. Hold that specific detail in mind, because it's the exact detail that makes what was eventually found inside Mars so genuinely startling. If we cannot dig deep enough to see inside a planet directly, how did anyone ever manage to map Earth's own interior at all? Let alone the interior of a planet 140 million miles away. The answer traces back to a specific, elegant property of seismic waves, the vibrations that radiate outward whenever rock suddenly breaks, or whenever something massive strikes a planet's surface with enough force to shake the ground around it. These waves travel in two fundamentally different modes, and the distinction between them turns out to be the single master key that eventually unlocked the interior of an entire world. The first kind are called P waves, short for primary or compressional waves. They are the fastest seismic waves that exist, traveling the way a sudden shove travels down a stretched-out slinky spring. Particles of rock are alternately compressed together and stretched apart, directly along the same line the wave itself is traveling. Critically, P waves can pass through solids, through liquids, and even through gases. Nothing about their basic physics requires the material they're moving through to hold any particular shape. The second kind are called S waves, short for secondary or shear waves. They travel more slowly than P waves, and they move differently. Particles shift sideways, perpendicular to the wave's direction of travel, the way a length of rope ripples when you flick one end of it sharply. And S waves have a genuinely crucial limitation, one that turns out to matter more than almost anything else in this entire story. They cannot travel through liquids at all. A liquid, by its basic physical nature, has no rigidity to shear against. There's nothing for a sideways moving wave to actually push against and transmit its motion through, the way there is in a solid. That single asymmetry. Swaves pass through solids, but are completely blocked by liquids, is the master key that has unlocked the interior of every planet we've ever managed to seismically study, including, eventually, Mars. The full unraveling of Earth's own interior using exactly this principle took the better part of 4 decades, and the story of how it happened is worth spending real time with, because the people responsible for it were, each in their own way, working with remarkably limited tools, doing something genuinely close to detective work with nothing but faint lines on paper. It began with Richard Dixon Oldham, a geologist studying the aftermath of 2 major earthquakes. First, the great 1897 Assam earthquake, and later California's catastrophic 1906 San Francisco earthquake. Poring carefully over seismic records from stations scattered around the globe, Oldham became the first person to clearly identify separate, distinct arrivals of P waves and S waves in the recorded data. Two different signals moving at two different speeds from the exact same initial event. And in 1906, based on careful analysis of exactly how those two wave types behaved as they traveled across the planet, he became the first scientist to argue, with genuine confidence, that Earth possessed a distinct, physically separate central core. 3 years later, in 1909, a Croatian scientist named Andrija Mohorovičić was studying the seismic records of an earthquake in his own region's Kupa Valley, and noticed something that at first seemed like a simple anomaly. Rather than a single clean arrival, the seismic waves appeared to arrive at distant recording stations in two separate pulses. One set travelling more slowly, having taken a direct path near the surface, and a second, faster set, which appeared to have been refracted, bent, by some considerably denser layer lying deeper underground. He had discovered, without ever being able to see it directly, the sharp physical boundary separating Earth's thin outer crust from the far denser mantle material beneath it, a boundary that geologists still call, in his honour, simply the Moho. In 1913, a German-American seismologist named Benno Gutenberg identified something genuinely strange in the global pattern of earthquake data. A distinct band, stretching roughly from 103 to 142 degrees of angular distance around any given earthquake's epicenter, were S waves. The shear waves that cannot pass through liquid, simply vanished from the recorded data entirely. They weren't merely weaker in that zone. They were completely absent. The only explanation that made physical sense was that something deep inside the Earth, directly in the path those particular S waves would otherwise have travelled, was liquid, blocking them completely, the same way liquid water blocks the passage of a shear wave in any laboratory sample. Gutenberg had located indirectly, through nothing but the specific absence of a signal, the outer boundary of Earth's molten outer core. And then, in 1936, a Danish seismologist named Inge Lehmann published a short, quietly extraordinary paper titled with characteristic understatement simply P prime. Lehmann had noticed something that, according to the prevailing models of the time, shouldn't have existed at all. Faint P-wave arrivals, showing up inside the region where Gutenberg's earlier work said P-waves should have been bent away and effectively hidden from detection. Working largely alone, at a time when women in the field of geophysics were a genuine statistical rarity, with none of the computational tools a modern seismologist would take for granted, Lehmann worked out, through careful, patient geometric reasoning, that these faint, unexpected signals could only be explained by a second, sharper boundary deep inside Earth's already discovered molten outer core. A distinct, solid ball of material, sitting at the very center of the planet, refracting those faint P-waves in exactly the pattern she was observing. She had discovered Earth's solid inner core, nested inside the liquid outer core, essentially by refusing to dismiss a handful of faint, inconvenient data points that a less careful researcher might easily have written off as simple noise. Oldham, Mohorovičić, Gutenberg, Lehmann. 4 scientists, working across 4 decades, each building carefully on the work of the last, none of them ever once directly touching, or even directly seeing, the layers they were describing. They built the complete 4-layer architecture of our entire planet's interior. Crust, mantle, outer core, inner core, using nothing but careful attention to how vibrations moved, and sometimes conspicuously failed to move, through solid rock they could never once physically access. This is shocking discovery number 1, in its own quiet way. Humanity's entire, detailed understanding of what lies beneath our own feet was built not by digging, but by listening. Patiently, carefully, across generations, to whispers travelling through solid rock from earthquakes that had already finished happening by the time anyone analysed the data. Modern seismic tomography, a considerably more advanced descendant of this same basic technique, now drawing on data from thousands of recording stations scattered across the globe simultaneously, can resolve Earth's interior structure down to a precision of mere tens of kilometers, revealing ancient slabs of ocean floor, subducted long ago, still slowly sinking through the mantle, and enormous plumes of hot material rising back up from the boundary between mantle and core. All of it, still, built from nothing but sound. Here's the natural next question, and it's exactly the one a small team of scientists and engineers spent decades working to answer. If listening carefully enough can reveal the entire interior structure of our own planet, could the exact same basic technique work on a completely different world, 140 million miles away? The mission built to test that idea was called InSight, a name constructed in the tradition of many NASA missions from a careful acronym: Interior Exploration Using Seismic Investigations, Geodesy and Heat Transport. It was formally selected in 2012 as the 12th mission in NASA's Discovery program, a deliberately cost-capped line of focused planetary science missions, each one built around answering a small number of carefully chosen, high-value scientific questions rather than attempting to do everything at once. The original plan called for a launch in March of 2016, but in December 2015, with the spacecraft already well into its final construction and testing, engineers discovered a serious, specific flaw: a vacuum leak in the evacuated titanium sphere at the heart of the mission's primary instrument. A defect the extraordinarily sensitive French-built seismometer inside simply could not tolerate. The instrument needed a genuine, sealed vacuum around its most delicate internal components to achieve the sensitivity the whole mission depended on, and that vacuum was leaking. There was no way to fix it in time for the planned 2016 launch window. The mission would have to wait for the next viable Earth-to-Mars trajectory, more than 2 years later, in 2018. That delay came with a real cost, both in time and in money. Repairing the instrument and waiting for the new launch window added an additional $153.8 million to a mission that had originally been budgeted at $675 million, bringing the total cost of the program to roughly $830 million, a genuinely significant sum invested entirely on the strength of a scientific bet that listening to a single, distant, silent planet for long enough and carefully enough would be worth the wait. The instrument itself, once finally completed and repaired, was a genuine international collaboration, spread deliberately across 3 continents. The core seismometer, called SEAS, the Seismic Experiment for Interior Structure, was built by France's National Space Agency, CNES, with its lead scientist based at the Institut de Physique du Globe de Paris, and additional contributions arriving from the Max Planck Institute in Germany, ETH Zurich in Switzerland, and Imperial College London, Oxford University, and NASA's own Jet Propulsion Laboratory. A second instrument, called HP Cubed, the Heat Flow and Physical Properties package, designed to measure heat escaping directly from Mars' interior, was built by Germany's DLR Space Agency. A third experiment, called RISE, designed to measure the planet's rotation with extraordinary precision using nothing but patient radio tracking, was built by NASA and JPL directly. And the spacecraft itself, the vehicle that would actually carry all of this instrumentation safely to the Martian surface, was constructed by Lockheed Martin Space in Denver, Colorado. InSight finally launched on May 5, 2018, lifting off from Vandenberg Air Force Base on the California coast. Notably, the very first interplanetary mission ever launched from America's west coast, rather than from the more traditional Florida launch sites. And on November 26, 2018, at 1:95:259 UTC, after a journey of roughly 6.5 months across the gulf of space separating Earth and Mars, the spacecraft plunged into the thin Martian atmosphere at a speed of 5.5 kilometers per second. What followed is a sequence engineers have long nicknamed, with a certain dark humor, 7 minutes of terror. The compressed, unforgiving span of time during which a spacecraft traveling at hypersonic speed has to decelerate, using nothing but a heat shield, a supersonic parachute, and a carefully timed sequence of retro-rockets from thousands of miles per hour down to a gentle touchdown, entirely on its own, with no possibility of any human intervention or correction, because the radio signal confirming success or failure wouldn't even reach Earth until minutes after the outcome. Whichever it turned out to be, had already been decided. 6 minutes after atmospheric entry, InSight touched down safely on Elysium Planitia, a flat, unremarkable equatorial plain at 4.5 degrees north latitude, 135.9 degrees east longitude. Mission control at JPL erupted into the kind of relieved, disbelieving cheering that has become almost a ritual signature of successful Mars landings. Elysium Planitia was chosen with a specific, deliberately unglamorous kind of care. It needed to be flat enough that the lander wouldn't risk tipping over on touchdown. It needed to sit at a low enough elevation that the thin Martian atmosphere above it would provide the parachute with just enough extra distance to meaningfully slow the spacecraft down. It needed to be close enough to the equator to guarantee continuous, reliable solar power throughout the mission. And critically, it needed to be dusty and relatively rock-free. Because unlike a rover, built to actively drive across rough, boulder-strewn terrain, InSight needed a patch of open, gentle ground smooth enough that its robotic arm could reach out and lay a genuinely delicate seismometer directly onto the surface, undisturbed by nearby rocks or slopes. On December 19, 2018, less than a month after landing, InSight's robotic arm carefully lifted the Sears seismometer and placed it directly onto the Martian surface. The very first seismometer ever deployed onto the surface of another planet by any spacecraft, anywhere, in the entire history of space exploration. On February 2nd, 2019, the team covered it with a specially designed wind and thermal shield, a domed, chainmail-like fabric skirt engineered specifically to dampen the disruptive effects of Martian wind gusts and the planet's own dramatic daily temperature swings, both of which would otherwise have swamped the instrument's exquisitely sensitive readings with meaningless noise. And exquisitely sensitive is, if anything, an understatement. SEAS's internal sensors, floating on precisely balanced, evacuated titanium bellows, were engineered to register ground displacements smaller than the diameter of a single hydrogen atom. CNES's own official specifications describe a sensitivity down to roughly half the radius of a hydrogen atom, something on the order of 0.5 angstroms or 50 trillionths of a meter. It is genuinely difficult to translate a number that small into anything resembling ordinary human intuition. It is, for all practical purposes, an instrument capable of detecting the seismic equivalent of a single falling grain of sand somewhere on the far side of an entire planet. But not everything about InSight's mission went according to plan, and one particular failure carries real emotional weight, worth sitting with directly, because it represents the genuine cost of attempting something this ambitious for the very first time. Alongside the seismometer, InSight also carried an instrument called HP Cubed, nicknamed, with obvious affection, the Mole. Designed and built by Germany's DLR space agency, it was intended to hammer itself steadily downward into the Martian soil, dragging behind it a long string of temperature sensors, eventually reaching a depth of roughly 5 meters, deep enough to directly measure the faint trickle of heat still escaping from Mars' own ancient interior. On its very first hammering session in February 2019, the Mole got stuck. Not because of any flaw in its engineering, but because of the soil itself. The regolith at Elysium Planitia turned out to have considerably lower cohesion and considerably less internal friction than mission planners had anticipated based on the best available pre-mission models. Without enough surrounding soil resistance to grip against, the self-hammering Mole simply couldn't generate the traction it needed to drive itself forward. Instead, with every hammer stroke, it bounced awkwardly in place, sometimes popping partway back out of the very hole it had been trying to dig. For 2 full years, Engineers at DLR and JPL improvised, testing solution after solution nobody had ever planned for in advance. They pressed the flat scoop of the robotic arm directly against the mole's side, hoping to provide the missing friction manually. They refilled its shallow pit with additional soil, hoping added weight and pressure might help. They tried a technique nicknamed chuffing, carefully scraping and compacting the surface material around the hole. Nothing worked reliably. In January 2021, NASA formally, officially abandoned the HP-cubed experiment. Its lead designer, Tilman Spohn, later described the failure as the hardest engineering defeat of his entire career. A uniquely painful kind of loss, watching a well-designed, carefully tested instrument fail, not because of any flaw in its own construction, but because of soil conditions on an entirely different planet that nobody could have fully anticipated in advance. Despite the mole's heartbreaking failure, SEAS itself worked beautifully, and on April 6, 2019, the 128th Martian day, or SOL, of the mission, it detected something genuinely historic. A faint, unmistakable seismic signal, rising clearly above the instrument's background noise. It was the first quake ever directly recorded on the surface of another planet. Over the following months, the catalogue of detected events began to steadily grow. By late 2019, researchers had identified 174 separate Marsquakes, which they began sorting into two broad families. Roughly 150 smaller, higher frequency events, apparently originating relatively close to the surface in the planet's brittle upper crust, and 24 lower frequency events, apparently originating from considerably deeper within the planet. In March 2021, SEAS recorded two sizable quakes, registering magnitudes 3.3 and 3.1, both traced back to a specific region called Cerberus Fossae, a set of young geological fissures east of the InSight landing site that would go on to become the single most seismically active region ever identified on Mars. Then, on December 24, 2021, SEAS recorded something genuinely unprecedented, a magnitude 4 event that, when researchers cross-checked its timing and estimated location against orbital imagery from NASA's Mars Reconnaissance Orbiter, turned out to correspond directly to a fresh meteoroid impact. A brand new crater, roughly 150 meters across, photographed from orbit almost exactly where the seismic data predicted it should be. It was the first time in the entire history of space exploration that a seismic event detected on another planet had been independently confirmed and cross-referenced against direct orbital imagery of the very impact that caused it. Two completely different scientific instruments, one listening from the ground and one watching from orbit, converging on the exact same violent event. And then, on May 4th, 2022, Sol 1222 of the mission, SEAS recorded the largest quake it would ever detect. Seismograms lit up dramatically at monitoring stations as far away as ETH Zurich in Switzerland, where much of the mission's seismic data was being carefully analysed. The InSight team's initial estimate placed the magnitude at a genuinely striking 5.0. Later, more careful analysis, published by an Oxford-led research team in 2023, refined that figure downward slightly to a magnitude of 4.7, while also settling a separate open question. This particular monster quake, unlike the December 2021 event, was not the result of any meteoroid impact at all. It was purely tectonic, a direct release of accumulated stress deep within the Martian crust itself, the single largest such release ever directly measured on another world. By the time the mission finally concluded, the complete Marsquake service catalogue contained 1,319 separate detected events, including 6 confirmed meteorite impacts and well over 1,000 additional smaller, higher frequency signals, each one a genuine, individual whisper from somewhere deep inside an entire planet's own quietly settling interior. But even as the scientific catalogue grew richer, the mission itself was slowly, visibly dying. not from any sudden failure, but from the same slow, patient enemy that has claimed nearly every solar-powered mission ever sent to the Martian surface: dust. Over months and then years, a fine layer of Martian dust steadily accumulated across InSight's solar panels, gradually reducing the sunlight reaching its power system. By mid-2021, the accumulation had become severe enough that engineers, in a genuinely inventive last resort, began deliberately trickling loose sand from the lander's own robotic scoop over the edges of the solar panels, hoping that occasional Martian wind gusts might catch enough of the falling sand to scour some of the accumulated dust away as it passed. The trick worked, to a modest degree, buying the mission a few additional months of operation. But the one thing that had kept earlier solar-powered rovers like Spirit and Opportunity alive for years beyond their planned lifespans: a passing dust devil, a small Martian whirlwind, powerful enough to sweep a solar panel genuinely clean, never once arrived to rescue InSight. Its available power dropped steadily from roughly 5,000 watt-hours per Martian day at the moment of landing, down to a mere few hundred watt-hours per day by the autumn of 2022. On April 24, 2022, Sol 1211, InSight captured its final self-portrait, its once gleaming solar panels now barely distinguishable from the reddish dust settled directly on top of them. On December 19, 2022, mission controllers recorded 2 consecutive missed communication sessions in a row. NASA formally announced the end of the mission. The final confirmed contact with the spacecraft had actually occurred several days earlier, on December 15th. On December 21st, 2022, NASA officially declared InSight retired. The lander's final social media post, written by the mission's communications team in InSight's own established, gently first-person voice, reads simply, "My power's really low, so this may be the last image I can send. Don't worry about me though. My time here has been both productive and serene." Here is something genuinely worth understanding about how a mission like InSight actually produces scientific knowledge, because it reshapes how we should think about a dead spacecraft's ongoing legacy. InSight, across its roughly 4 years of active listening, gathered so much raw seismic data that the genuine scientific work of carefully analyzing it, extracting real, defensible conclusions from faint, often ambiguous signals, continued for years after the lander itself had gone permanently silent. The 2023 Nature paper establishing the size of Mars' core. A separate 2023 Nature paper revealing an entirely unexpected molten layer sitting directly above that core. The 2023 Oxford Lead study finally confirming the true tectonic origin of the enormous May 2022 quake. A 2025 Nature paper announcing the detection of a solid inner core nested even deeper inside the already discovered liquid outer core. And, arriving in that same remarkable year, the discovery that sits at the very center of tonight's entire story. The 2025 science paper revealing that Mars' mantle isn't smooth at all, but genuinely, chaotically lumpy. Every single one of these discoveries was written entirely from archived seismograms, recorded by a spacecraft that had already been dead, sitting silent and dust-covered on the Martian surface, for months or years by the time each individual paper was finally published. Members of the InSight science team have estimated that a full decade's worth of additional, unpublished discovery may still remain buried inside the mission's complete archived dataset, waiting patiently for future researchers to finally extract it. A single, continuous, 4-year conversation with a distant, silent planet. And we are, even now, still in the process of properly listening back to everything it actually said. Before InSight, everything scientists believed about Mars' interior came entirely from indirect sources. Meteorites that had, at some point in the deep past, been violently ejected from the Martian surface and eventually landed on Earth. Broad, aggregate gravity measurements taken from orbiting spacecraft, and theoretical models built from careful extrapolation rather than direct observation. Estimates for the thickness of Mars' crust, before any direct seismic measurement existed, ranged anywhere from 20 to 100 kilometers, an enormous span of uncertainty. Whether the planet's core was solid, liquid, or some mixture of both remained genuinely, completely unknown. The mantle, in every meaningful sense, remained a total black box. Not one of these figures had ever come from an actual, direct physical measurement. In July 2021, a research team led by Brigitte Knapmeyer-Endrun published the first definitive crustal structure results in the journal Science, drawing directly on InSight's accumulated seismic data. Beneath the InSight landing site itself, the crust appeared to be either approximately 20 kilometers thick if modeled as two distinct layers, or approximately 39 kilometers thick if modeled as three, and averaged across the entire planet. The best current estimate places Mars' crust somewhere between 24 and 72 kilometers thick, generally thinner than most pre-mission predictions had assumed. This new, precise measurement immediately connected to one of the largest, oldest unsolved puzzles in all of Mars science: the planet's dramatic hemispheric dichotomy. Mars' northern hemisphere is smooth, relatively low in elevation, and comparatively thin-crusted. Its southern hemisphere is heavily cratered, considerably higher in elevation and noticeably thicker crusted, with an overall elevation difference between the two hemispheres of roughly 5 to 6 kilometers. Three competing hypotheses currently attempt to explain this dramatic asymmetry. A single, colossal impact, delivered by an object somewhere between the size of Pluto and Earth's own moon, early in Mars history, violently excavating an entire hemisphere-scale basin all at once. The cumulative effect of multiple separate large impacts over time, rather than one single event, or a specific pattern of internal mantle convection, sometimes called degree 1 convection, which could have gradually, over enormous spans of time, dragged and thinned the crust preferentially toward one side of the planet. The debate remains genuinely unresolved, and InSight's new, precisely measured crustal thickness data is now actively being incorporated into the next generation of competing models attempting to finally settle it. Deeper still, InSight determined that Mars' mantle extends down to a depth of roughly 1,560 kilometers, with an unusually thick lithosphere, the rigid, cold outer layer that sits directly beneath the crust, reaching close to 500 kilometers in depth, as if Mars had built up an unusually stiff, rigid outer shell early in its history, one that has actively suppressed vigorous mantle convection ever since. The mantle's composition, as best current analysis can determine, is dominated by iron and magnesium-rich silicate minerals. Principally olivine and pyroxene, the exact same basic mineral families that make up the bulk of Earth's own mantle, with smaller quantities of aluminum, calcium, and potassium mixed throughout. Interior temperatures at the very top of this mantle layer can reach roughly 1,500 degrees Celsius. The story of Mars' own core turned out to unfold across three separate, genuinely surprising chapters, each one arriving years apart, each one revealing something the previous chapter hadn't anticipated. The first chapter arrived in July 2021 in a separate science paper led by researcher Simon Staler. Using careful analysis of S-wave reflections bouncing directly off the boundary between Mars' mantle and its core, the InSight team calculated the radius of Mars' liquid metallic core at 1,830 kilometers, plus or minus about 40 kilometers, genuinely larger than most pre-mission theoretical models had predicted, implying that a considerably greater fraction of the entire planet's total mass was concentrated in its core than scientists had generally assumed. The second chapter arrived roughly 2 years later, in October 2023, when two independent research teams, one led by Amir Khan, the other by Henri Samuel, each published separate papers in Nature, working from an expanded, more carefully reanalyzed catalogue of Marsquake events. Both teams arrived, independently, at a genuinely startling revision, what had originally been measured and described as a single, uniform, liquid metallic core wasn't actually uniform at all. Sitting directly on top of a smaller, genuinely metallic inner region, researchers discovered an entirely unexpected additional layer, a roughly 150-kilometer thick shell of molten silicate rock. Essentially an enormous, planet-spanning sea of magma, sandwiched directly between Mars' rocky mantle above and its true metallic core below. With this newly discovered layer properly accounted for, the actual metallic core itself shrank considerably, down to a revised radius of 1,675 kilometers, plus or minus 30 kilometers. Smaller than the original 2021 estimate, but genuinely denser and remarkably enriched with lighter elements, principally sulfur, but also meaningful quantities of oxygen, carbon, and hydrogen, mixed directly into what had originally been assumed to be a relatively simple iron-nickel alloy. The third confirming chapter, published slightly earlier that same year, in June 2023, came from an entirely different measurement technique altogether, the RISE experiment. The radio tracking instrument built by NASA and JPL, rather than the seismometer built by NES, had spent years patiently measuring Mars' own precession. The slow, subtle conical wobble every rotating planet's spin axis naturally undergoes over time, because the rate of that wobble depends directly on how mass is actually distributed inside the planet, and specifically on the size of any dense metallic core buried at its center. A research team led by Sébastien Lemaistre was able to calculate an entirely independent estimate of Mars' core radius, using nothing but exquisitely precise measurements of the lander's own radio signal, Doppler shifted, by fractions of a nanometer per second as Mars itself wobbled beneath it. Their result, a core radius of 1,835 kilometers, plus or minus 55 kilometers, and confirmation that the core is indeed genuinely liquid. A completely independent measurement using an entirely different physical principle, arriving at a figure remarkably close to what the seismic team had already found using sound alone. And then, in September 2025, arriving in the same remarkable year as tonight's central discovery, a research team led by Daoyuan Bi published a further refinement in Nature, seismic waves passing through and reflecting off deep interfaces within that already discovered liquid core suggested the presence of a further, previously undetected solid inner core, nested at the very center of everything, with an estimated radius of 613 kilometers, plus or minus 67 kilometers. Taken together, these three separate chapters reveal something genuinely remarkable. Mars, it turns out, shares the same basic nested architecture as Earth, an outer liquid metallic layer wrapped around an inner solid metallic core, but frozen, in a very real sense, at an earlier, less fully differentiated stage of the exact same fundamental planetary process that produced our own, considerably more thoroughly sorted planet. There's a specific piece of physical evidence, written directly into the rocks of Mars' own southern highlands, that connects everything we've covered so far into a single, coherent, genuinely sobering story. Certain ancient rocks in Mars' southern hemisphere carry a faint but genuine, permanent magnetization. Direct physical proof that Mars, at some point deep in its own past, possessed an active global magnetic field, generated by the same basic physical mechanism that still powers Earth's own magnetic field today. A churning, electrically conducting liquid core, convecting vigorously enough to sustain what scientists call a dynamo. That ancient Martian dynamo appears to have died roughly 4 billion years ago, as the planet's outer core gradually cooled below the specific temperature threshold required to sustain the kind of vigorous internal convection a working dynamo genuinely depends on. Without a global magnetic field standing guard, Mars lost its single most important line of defense against the relentless pressure of the solar wind. The continuous stream of charged particles flowing outward from the Sun at extraordinary speed in every direction. NASA's MAVEN orbiter, studying this exact process directly, has confirmed that Mars continues losing hydrogen from its uppermost atmosphere to this day, at a rate that varies by a full order of magnitude depending on the Sun's own 11-year activity cycle. And that, across the full span of Martian history, the planet has lost water equivalent to an entire global ocean, stripped away steadily, atom by atom, over billions of years. The full chain of causation, worth stating plainly and in order, runs like this. Mars was a comparatively small planet. Because it was small, its interior cooled comparatively quickly. As its interior cooled, the vigorous convection driving its core's dynamo eventually collapsed. As the dynamo collapsed, Mars' global magnetic shield disappeared. Without that magnetic shield, the relentless solar wind began directly eroding the planet's own atmosphere. As the atmosphere thinned, Mars' water. The very thing that once carved the ancient river valleys and lake deltas we can still see clearly in orbital photographs today, escaped steadily into space. And the eventual result, after billions of years of this same slow, patient, entirely physics-driven process, is the frozen, nearly airless desert world we observe today. Every single link in that chain follows, with genuine physical inevitability from the very first one. Mars, quite simply, was never big enough to keep its own interior running. Now we arrive at the discovery this entire story has been building toward. The finding that gives tonight's exploration its title, and the one that genuinely surprised even the scientists who found it. The formal paper, titled Seismic Evidence for a Highly Heterogeneous Martian Mantle, was published in the journal Science on August 28, 2025, appearing in volume 389, issue 6763. Its lead author was Dr. Konstantinos Charalambous, of the Department of Electrical and Electronic Engineering at Imperial College London, working alongside co-authors including Professor Tom Pike, also of Imperial College London, and Dr. Mark Panning of NASA's Jet Propulsion Laboratory, who had previously served directly as the InSight mission's own project scientist. The research team focused their attention on 8 exceptionally clear Marsquakes drawn from the full 4-year catalogue, including, notably, the 2 confirmed meteoroid impact events, whose precise timing and location were already independently known from orbital photography of their resulting craters, providing an unusually reliable, well-constrained starting point for everything the team went on to measure. What made these particular 8 events genuinely useful was that they contained unusually strong, well-preserved high-frequency energy. Seismic signals that had travelled from Mars' crust, deep down into the mantle, and back up again to sea ice's weighting sensors, all while still retaining enough fine detail to reveal genuinely small-scale internal structure. Higher frequency waves, as a general rule in seismology, are meaningfully more sensitive to small, localized variations in the material they're passing through than the lower frequency waves that dominate most ordinary Marsquake signals. When Charalambous and Pike carefully compared the precise arrival times of these high-frequency signals against one another, they noticed something that, at first, made no immediate sense. The farther any given wave had travelled through Mars' mantle before finally reaching seas, the more its highest frequency components appeared to lag noticeably behind. As Pike later described the moment of realization directly, "When we first saw this in our quake data, we thought the slowdowns were happening in the Martian crust. But then we noticed that the farther seismic waves travel through the mantle, the more these high-frequency signals were being delayed." The team ran extensive, planet-wide computer simulations, carefully modelling how seismic waves should be expected to propagate through a mantle of Mars' known overall composition and structure, and found that the specific scattering pattern they'd actually observed in the real data simply could not be produced by a smooth, uniform mantle, no matter how the simulation's parameters were adjusted. The only physical explanation that consistently reproduced the observed pattern involved localized regions scattered throughout the mantle, each one compositionally distinct from the surrounding material around it. Pockets, essentially, of a genuinely different substance, embedded directly within the broader silicate mantle. The specific findings, once fully quantified, were genuinely striking. Kilometre-scale heterogeneities distributed throughout the mantle rather than confined to any single depth or region, with individual fragments reaching sizes of up to roughly 4 kilometres across. Critically, the sizes of these fragments followed what scientists call a fractal distribution, a specific, recognizable mathematical pattern featuring a small number of larger fragments, alongside a considerably larger number of progressively smaller ones, following a consistent, self-similar scaling relationship across every size range measured. Tom Pike offered a genuinely vivid, accessible description of exactly what that fractal pattern actually represents. What we are seeing is a fractal distribution, which happens when the energy from a cataclysmic collision overwhelms the strength of an object. You see the same effect when a glass falls onto a tiled floor as when a meteorite collides with a planet. It breaks into a few big shards and a large number of smaller pieces. It's remarkable that we can still detect this distribution today. A wine glass dropped onto a hard floor. A meteorite striking a planet's surface. Two events, wildly different in scale, that nonetheless shatter according to the exact same underlying mathematical rule. And, remarkably, that same precise fractal signature discovered inside the mantle of an entire planet, 4.5 billion years after whatever violent event originally produced it. To understand why finding kilometre-scale fragments deep inside Mars' mantle is so genuinely surprising, it helps to understand the specific violent process that likely created them in the first place, and why that same process, on Earth, left behind essentially no comparable trace. Charalambous and his research team interpret these mantle fragments as genuine physical remnants of the earliest, most violent chapter of the entire solar system's formation, a period lasting roughly the first 100 million years after the Sun itself ignited, during which the young inner solar system remained genuinely crowded with leftover planetesimals and even small, partially formed protoplanets, still colliding with the newly forming rocky worlds around them. The general picture, as researchers currently understand it, unfolds something like this. As Mars was still actively assembling itself from surrounding debris, it was repeatedly struck by these massive leftover impactors. Collisions energetic enough to melt entire, continent-sized regions of the young planet's surface into vast, roiling oceans of liquid magma. Material from the impactors themselves, often colder, denser, and chemically distinct from Mars' own native material, plunged directly into these molten oceans. Some of that impactor material, being sufficiently dense, sank all the way down toward the newly forming core. But other fragments, either chemically buoyant enough to resist sinking further, or simply too viscous and compositionally different to fully blend and homogenize with the surrounding magma, instead became genuinely trapped, suspended partway through the process, as the magma ocean gradually cooled and crystallized into solid mantle rock around them. On Earth, this exact same fundamental violent process almost certainly occurred as well. Our own planet, if anything, endured an even more dramatic version of it, including the truly colossal impact, roughly 4.5 billion years ago, of a Mars-sized protoplanet often referred to as Theia, an event so energetic it is widely believed to have generated the material that eventually coalesced into our own Moon. But Earth's mantle has continued convecting, vigorously and continuously, for the entire 4.5 billion years since that original chaos, steadily subducting ancient crust back down into the deep interior at boundaries like the modern Cascadia subduction zone off North America's own Pacific coast, thoroughly mixing and remixing its own internal material at a scale of hundreds of millions of years. Any comparable fragments of debris left over from Earth's own violent formation would almost certainly have been smoothed, chemically dissolved, and thoroughly remixed away long ago. Mars followed a genuinely different path. As Charalambous himself put it directly, what happened on Mars is that, after those early events, the surface solidified into a stagnant lid. It sealed off the mantle beneath, locking in those ancient chaotic features like a planetary time capsule. That specific phrase, a planetary time capsule, captures the entire discovery with real precision. Mars, unlike Earth, developed what geologists call a stagnant lid, a single, unbroken, rigid outer shell with no internal plate boundaries, no ongoing subduction, none of the vigorous, continuous internal churning that has kept Earth's own mantle so thoroughly, patiently mixed across its entire multi-billion-year history. Once that stagnant lid fully formed, whatever chaotic debris happened to be trapped inside Mars' mantle at that specific moment was, in a very real sense, sealed in place. Left essentially undisturbed for the following 4.5 billion years, waiting patiently for an instrument sensitive enough to finally detect it. Charalambous elaborated further on exactly what that means for how we should understand these findings. These colossal impacts unleashed enough energy to melt large parts of the young planet into vast magma oceans. As those magma oceans cooled and crystallized, they left behind compositionally distinct chunks of material. And we believe it's these we're now detecting deep inside Mars. And separately, reflecting on how much sharper this detection turned out to be than anyone had genuinely anticipated going in. We've never seen the inside of a planet in such fine detail and clarity before. What we're seeing is a mantle studded with ancient fragments. Their survival to this day tells us Mars' mantle has evolved sluggishly over billions of years. On Earth, features like these may well have been largely erased. Dr. Mark Panning, reflecting on the discovery from his own vantage point as the mission's former project scientist, offered a fitting summary of what this entire chapter of ongoing analysis actually represents. InSight's data continues to reshape how we think about the formation of rocky planets, and Mars in particular. It's exciting to see scientists making new discoveries with the quakes we detected. And Tom Pike, reflecting on just how much sharper this particular result turned out to be than the mission's own original expectations. We knew Mars was a time capsule bearing records of its early formation, but we didn't anticipate just how clearly we'd be able to see with InSight. It's worth being genuinely honest, in the spirit of careful scientific reporting, about exactly how settled this specific interpretation currently is. The impactor fragment explanation represents the research team's own best current interpretation of the data. The specific hypothesis that most consistently and completely explains the fractal size distribution and the wide depth range across which these heterogeneities were detected. But legitimate alternative explanations remain on the table and haven't yet been fully ruled out. The observed patchiness could, alternatively, reflect compositional layering produced by fractional crystallization of the original magma ocean itself, rather than genuine injected debris from outside impactors. It could reflect localized pockets of partial melt, though the fact that the 8 source events span multiple depths and multiple directions through the planet does meaningfully argue against this particular explanation. It could reflect chemical heterogeneities inherited more generally from the inherently uneven, stochastic process of planetary accretion itself, rather than from any specific identifiable impact events. A future Mars seismic network. Multiple simultaneous listening stations spread across different regions of the planet, rather than the single lonely instrument InSight actually provided, would be required to genuinely settle these open questions with full confidence, resolving the true three-dimensional geometry of these fragments in a way a single station, however sensitive, simply cannot achieve, entirely on its own. This is shocking discovery number 1 of tonight's central act, and it deserves to sit with you fully. Buried between roughly 900 and 1400 kilometers beneath the red dust of Mars, sit the physical, compositionally distinct remnants of the same violent process that built the entire solar system. Survivors of a chaos so ancient it predates nearly everything else we know how to measure, preserved not because anyone planned for their preservation, but simply because the planet holding them stopped stirring itself long enough to let them settle, undisturbed, for 4.5 billion years. Let's turn now, for the remainder of tonight's exploration, toward the surface of Mars, and specifically toward the single most enormous structure anywhere in our entire solar system, because a separate, independent discovery made using an entirely different method suggests it may not be quite as dead and dormant as textbooks have long assumed. Olympus Mons rises approximately 22 kilometers above the surrounding Martian plains. Precise measurements from the Mars Orbiter Laser Altimeter place its summit at 21.287 kilometers above the planet's overall reference elevation. It spans roughly 600 kilometers across at its base, comparable in raw physical footprint to the entire size of the country of France or the US state of Arizona. Its outer edge is ringed by a sheer basal cliff, in places reaching as much as 8 kilometers in height, a vertical wall taller on its own than nearly every mountain range found anywhere on Earth. And its summit caldera, the great collapsed crater at its very peak, spans approximately 85 kilometers across on its own. For direct comparison, Mount Everest rises 8.85 kilometers above sea level. Measured from the surrounding seafloor rather than sea level, Hawaii's Mauna Loa, Earth's own largest shield volcano, rises approximately 10 kilometers. Olympus Mons stands roughly 2.5 times taller than Everest, and the actual difference in total physical volume between the two mountains is even more staggering than the height comparison alone suggests. And because its overall slope averages a genuinely gentle 5 degrees, spread across that entire 600-kilometer base, a person standing directly at the mountain's foot would not perceive anything resembling a typical mountain silhouette at all. The structure is so vast that it simply extends beyond the visible horizon in every direction. Olympus Mons does not stand alone. It forms part of the Tharsis Rise, an entire continent-sized volcanic bulge covering roughly a quarter of the Martian surface, hosting not only Olympus Mons itself but also 3 additional enormous volcanoes: Ascraeus, Pavonis, and Arsia Mons, collectively known as the Tharsis Montes, alongside dozens of smaller volcanic structures scattered throughout the same broad region. Volcanic activity across this entire region has continued, at some level, for genuinely billions of years, with the most recent large lava flows dated to somewhere between 100 and 200 million years ago. And individual fissures within the Cerberus Fossae system, the exact same region responsible for so many of the Marsquakes we discussed earlier, apparently active as recently as 50,000 years ago, a genuinely recent event on any meaningful geological timescale. For decades, the Tharsis region has presented planetary scientists with a genuine gravitational puzzle under ordinary, conventional geological theory. A principle called flexural isostasy. An enormous mass, like an entire continent-sized volcanic bulge, should press downward on the underlying crust, causing the surrounding lithosphere to sink slightly and the immediately adjacent regions to rebound gently upward in compensation. Tharsis does something close to the opposite. It sits unusually high and is surrounded by a ring-shaped region of noticeably weaker than expected gravity. A puzzling anomaly sometimes called a geoid annulus, which had genuinely baffled planetary geophysicists for decades. In September 2024, at the Europlanet Science Congress, Dr. Bart Root of TU Delft, working alongside colleagues at Utrecht University, announced a genuinely compelling candidate explanation, drawing directly on InSight's own gravity and seismic data, combined with additional gravity measurements gathered across multiple previous Mars missions. The resulting peer-reviewed paper was subsequently published in the Journal of Geophysical Research, Planets. The gravity anomaly beneath Tharsis, their analysis suggests, is best explained by an enormous mass of anomalously light material, roughly 1,750 kilometers wide, centered at a depth of approximately 1,100 kilometers beneath the surface. Interpreted as the rising head of an active mantle plume, a column of hot, buoyant, partially molten silicate rock actively ascending from deep within Mars' interior toward the base of its rigid outer lithosphere. Dr. Root described the finding directly. There seems to be a big mass, something light deep in Mars' layer, possibly rising from the mantle. It shows that Mars might still have active movements happening inside it, making new volcanic things on the surface. The very same broader gravity survey also revealed roughly 20 additional dense, previously hidden structures buried beneath ancient sediment in Mars' northern hemisphere. Regions measurably denser than their surroundings, possibly representing buried impact melt deposits or the remnants of extinct volcanic structures, entirely hidden from any direct surface observation. It's genuinely important, in the interest of full honesty, to be precise about exactly how confirmed this specific interpretation currently is. Gravity anomalies, by their basic mathematical nature, never have a single, uniquely determined solution. The same observed pattern of anomalous gravity can, in principle, be produced by more than one different underlying physical arrangement of mass. Roots light mass, rising plume interpretation, represents the most physically consistent explanation currently available, genuinely preferred by the research team based on everything else we know about Mars. But the same gravity signature could, in principle, also be explained by a compositionally distinct, low-density region of otherwise stationary residual mantle material, or by an unusually thick, low-density root extending downward from the crust itself, without requiring any active upward movement at all. The plume interpretation remains, honestly, a scientifically well-supported hypothesis, not yet a fully, independently confirmed physical fact. Sample return missions, additional seismic follow-up studies, and continued time series gravity monitoring, tracking how the anomaly itself might change over years, would all be needed to settle the question with genuine confidence. But if Root's interpretation does turn out to hold, if there truly is an active plume of buoyant, partially molten material still slowly rising beneath the largest volcano in the entire solar system, then Mars is not, in any meaningful sense, a fully, permanently dead world. It is, at most, a sleeping one. And that distinction opens genuinely serious questions worth sitting with directly. Could ongoing interactions between rising magma and buried subsurface ice currently be producing pockets of liquid brine, or localized geothermal heat somewhere beneath the Martian surface right now? Could that same rising plume eventually break through to the surface entirely, producing fresh, visible volcanic activity, perhaps millions of years from now, or perhaps, on the scale of an active mantle plume's own patient timeline, considerably sooner than that? And for any future human explorers eventually attempting to establish a lasting presence on Mars, could the flanks of Tharsis itself represent a genuinely valuable strategic resource? A source of accessible geothermal heat, subsurface water ice, and other useful volatile compounds concentrated in one identifiable region of the planet? Let's zoom out now and place everything we've learned about Mars specifically into the broader context of the entire inner solar system. Because Mars is not an isolated case study. It's one specific outcome among four of the exact same original formation process. All four of the solar system's rocky terrestrial planets, Mercury, Venus, Earth, and Mars, formed from the same protoplanetary disk of gas and dust surrounding our young sun roughly 4.5 billion years ago. And yet each one settled into an almost entirely different final state. Mercury, at just 4,879 kilometers across, sits closest to the sun, scorched, heavily cratered, entirely without any meaningful atmosphere, and possessing an anomalously large iron core, making up roughly 60% of the entire planet's total radius, a proportion considerably larger than any of its rocky siblings. Venus, nearly identical to Earth in overall physical size, developed into something close to a planetary nightmare instead. A crushing 92-bar atmosphere, surface temperatures reaching 460 degrees Celsius, clouds of genuine sulfuric acid, no meaningful magnetic field, and no evidence of active plate tectonics of any kind. Earth, at 12,742 kilometers across, developed oceans, active plate tectonics, a robust, continuously functioning magnetic field, and, as far as we currently know, is the only one of the four to have ever developed life. And Mars, at 6,779 kilometers across, roughly 53% of Earth's own diameter, and only about 10.7% of Earth's total mass, ended up frozen, dry, and, in every meaningful geological sense, seismically quiet. Why did these four genuinely similar starting points diverge so dramatically? Part of the answer comes down to something close to simple thermodynamics, a genuinely elegant, almost intuitive piece of physics. Smaller planets lose their internal heat considerably faster than larger ones, for a very specific geometric reason. Heat is lost through a planet's outer surface area, but stored throughout its entire internal volume. Surface area scales with the square of a planet's radius, volume scales with the cube. Halve a planet's radius, and you halve its overall ratio of stored volume to radiating surface area, meaning the smaller planet cools roughly twice as fast, relative to its own size, as its larger counterpart. Mars, at roughly half Earth's diameter and barely a tenth of its total mass, was, in a very real thermodynamic sense, doomed from the very beginning to freeze first among the four. Its interior stopped vigorously churning. Its dynamo eventually died, and everything that followed, the lost magnetic shield, the stripped atmosphere, the vanished surface water, cascaded directly, inevitably, from that single foundational fact of its own comparatively modest size. Mercury, smaller still, cooled even faster. Earth, considerably more massive than either, remains genuinely hot inside to this very day. There's a second, equally important factor worth understanding directly. Earth remains the only one of the four rocky planets we currently know to possess active, ongoing plate tectonics, the continuous churning, subducting, continent-shifting process that has kept our own mantle so thoroughly mixed and our own interior heat so effectively regulated across the entire span of our planet's history. Several factors likely combine to make this possible. Water itself plays a genuinely crucial role, chemically weakening, subducting crustal material and hydrating the surrounding mantle, enabling the kind of ductile, ongoing deformation plate tectonics fundamentally depends on. Our own moon-forming impact may have helped reset Earth's overall thermal state early on, and continues, even now, to provide meaningful tidal heating through its ongoing gravitational relationship with our planet. A specific feedback effect involving mineral grain size, where ongoing deformation itself progressively weakens the surrounding lithosphere further, likely also plays a role. And Earth simply happens to sit at close to an ideal overall size, large enough to retain substantial internal heat and sustain vigorous convection, yet still small enough for its outer shell to genuinely fracture into distinct, independently moving plates, rather than settling into one single, unbroken, rigid shell the way Mars evidently did. None of Mars' rocky siblings appear to have landed on that same precise combination of conditions. And because neither Mercury nor Venus has ever developed anything resembling active plate tectonics, both worlds may well preserve their own versions of exactly the kind of ancient, unmixed heterogeneity Mars has just revealed, buried deep within their own respective mantles, simply waiting for an instrument sensitive enough to eventually detect it. We may, in fact, get a genuine opportunity to test this exact prediction directly in the coming years. The joint European-Japanese Bepi-Colombo mission is scheduled to finally enter orbit around Mercury in November 2026, following a delay from its originally planned 2025 arrival caused by a 2024 thruster anomaly. While Bepi-Colombo does not carry a dedicated seismometer of its own, its extraordinarily precise laser altimetry and radio tracking instruments will meaningfully constrain Mercury's own interior structure and rotational behavior. NASA's Veritas mission to Venus, meanwhile, has been delayed to a 2031 launch following institutional funding difficulties at JPL, and ESA's separate Envision mission to the same planet remains scheduled for some time in the early 2030s. Neither of these two upcoming Venus missions currently carries any seismic instrument at all, meaning a genuine, direct test of the lumpy siblings prediction, at least for Venus specifically, would require an entirely new landed seismic package, currently existing only as an early-stage mission concept under active study at both NASA and ESA. And there's a final, genuinely important thread connecting all of tonight's story to something considerably larger still: the ongoing search for potentially habitable worlds orbiting entirely different stars. We cannot, with any currently foreseeable technology, physically listen to the interior of a planet 20 light-years away, but we can measure its overall bulk density, calculated from its total mass and physical radius. We can study its atmosphere, using the delicate technique of transmission spectroscopy, watching how starlight filters through it during a transit. And, if conditions genuinely align favorably, we may eventually be able to detect telltale signatures of ongoing atmospheric loss. Indirect evidence hinting at whether or not a distant world still possesses a functioning magnetic shield of its own. Mars, in this specific sense, serves as our most valuable and concrete anchor point, a real, directly measured example of precisely what happens when a genuinely rocky planet turns out to be too small to hold onto its own internal heat, its own protective magnetic field, its own atmosphere, and ultimately its own liquid water. Every single rocky exoplanet we will ever discover, sitting somewhere within its own star's habitable zone, exists somewhere along the exact same fundamental spectrum, bounded on one end by everything Mars ultimately lost, and on the other by everything Earth, against genuinely long odds, somehow managed to keep. Before we move toward tonight's closing reflection, it's worth pausing to state, clearly and directly, exactly how confident we should be in each of the major findings we've walked through. Because genuine scientific honesty requires distinguishing carefully between what has been firmly established and what remains a well-supported but still genuinely open hypothesis. The lumpy mantle discovery itself, at the very center of tonight's story, represents the single best current interpretation of a genuinely real, carefully measured seismic scattering pattern. But it remains, honestly, one interpretation among a small number of scientifically serious possibilities, rather than an absolutely settled, unchallengeable fact. The impact of fragment explanation fits the observed fractal size distribution, and the wide range of depths across which these heterogeneities were detected more completely and more naturally than any competing explanation currently on the table. But alternative interpretations, compositional layering left directly over from the original magma ocean's own crystallization process, rather than genuinely injected outside debris, scattered pockets of localized partial melt, or heterogeneities simply inherited from the inherently uneven, unpredictable process of accretion itself, have not been, and at this stage genuinely cannot yet be, fully and definitively ruled out. A future seismic network on Mars, involving multiple simultaneous listening stations spread across genuinely different regions of the planet, rather than InSight's single, solitary instrument, would be required to finally, decisively resolve the true three-dimensional geometry of these fragments with full scientific confidence. The Tharsis plume interpretation, similarly, represents a scientifically well-supported, genuinely preferred explanation for a real, carefully measured gravity anomaly. But gravity measurements, by their fundamental mathematical nature, are never uniquely solvable from a single dataset alone. The rising plume interpretation remains the current best explanation. It has not yet been independently, conclusively confirmed as an absolute, settled fact. And there's a further, more general limitation worth stating plainly, one that honestly applies to nearly every specific finding we've covered throughout tonight's entire exploration. InSight operated as a single station seismometer for its entire 4-year mission. It could never triangulate the precise location of any individual Marsquake using its own data alone, the way a genuine global network of multiple simultaneous stations easily can. Every single distance and directional estimate for every recorded Marsquake had to be carefully, painstakingly reconstructed from the timing gap between an event's P-wave and S-wave arrivals at that one single station, combined with additional, more subtle analysis of how surface waves and internal reflections happen to arrive. This is precisely why certain individual quake magnitudes were later revised, including, notably, the famous May 2022 monster quake, originally estimated at magnitude 5.0, later carefully refined down to magnitude 4.7, and why the lumpy mantle discovery itself ultimately required 8 separate, exceptionally clear seismic events and years of careful, patient reanalysis rather than emerging cleanly from any single dramatic measurement. None of this uncertainty diminishes what InSight actually achieved. If anything, it sharpens it. A single, lonely instrument, working entirely alone, with no partner station anywhere else on an entire planet to triangulate against, still managed to reveal a crust, a mantle, a molten silicate layer nobody had specifically predicted in advance, a liquid outer core, a newly detected solid inner core, and, sitting right at the very heart of everything we've covered tonight, kilometer-scale fragments of the solar system's own violent birth, still sitting there, remarkably undisturbed, after 4.5 billion years. Before we close, let's gather everything we've covered tonight, all together, and sit with the true scale of what actually happened here. Humanity's deepest physical dig into any planet, anywhere. The Kola Superdeep Borehole reached 12,262 meters into our own Earth, roughly 0.19% of the way to our own planet's center, stopped entirely by rock that simply refused to hold its own shape at the depths and temperatures involved. Our deepest continuous sample of genuine mantle material recovered from beneath the Atlantic seafloor at the Atlantis Massif in 2023 reaches barely 1.2 kilometers, and a single seismometer, built by a French space agency, sensitive enough to detect ground motion smaller than the width of a single hydrogen atom, sitting motionless and unaided on a flat, dusty plain roughly 140 million miles from the nearest human being, managed. Using nothing but the faint vibrations of an entire planet quietly settling itself, to map a crust, a mantle extending some 1,560 kilometers deep, a molten silicate layer nobody had specifically predicted, a liquid metallic core stretching 1,675 kilometers outward from the planet's center, and, quite possibly, a solid inner core nested at the very middle of everything else. And within that same painstakingly reconstructed structure, it detected something that, by every reasonable prior expectation, simply shouldn't still have been there at all. Kilometer-scale fragments of the solar system's own violent formation, preserved essentially untouched for 4.5 billion consecutive years inside the deep interior of an entire, still-standing world. Every one of these discoveries, gathered together, traces back to a genuinely small amount of total collected data. 4 years of intermittent listening using a single instrument at a single fixed location on a single planet. That is an extraordinarily small foundation to have completely reshaped our entire understanding of how rocky planets are actually born. There's something genuinely worth sitting with here, now that we've walked through this entire story together. Mars did not preserve these ancient fragments because anyone, or anything, ever intended for them to be preserved. It preserved them purely by accident, by simply being too small, too quick to cool, too quiet in its own deep interior, to ever fully erase the record of its own violent birth the way our own, considerably more geologically active planet eventually did. Every trace of Earth's own equivalent chaos. And there is every reason to believe Earth endured a genuinely comparable, if not more extreme, period of early bombardment, has long since been folded back down into the mantle, melted, remixed, and redistributed by 4.5 billion continuous years of vigorous plate tectonics, patiently erasing its own earliest history in the very same ongoing process that has kept our planet geologically and biologically so remarkably alive. There is a genuine, almost poetic irony sitting directly at the center of this entire discovery. The very quality that makes Mars, today, a frozen, seemingly lifeless world. Its comparatively small size, its early cooling interior, its long-dead magnetic dynamo, its stagnant, unmoving outer shell, is the exact same quality that allowed it to preserve a genuinely irreplaceable record of the solar system's own earliest, most violent history. Earth, by staying geologically alive, quietly erased its own baby pictures. Mars, by dying early, accidentally became the only planetary archive we currently have access to. And there's a further, genuinely humbling layer worth sitting with directly. We didn't recover this ancient record by digging for it, the way we might excavate a genuine archaeological site here on Earth. We recovered it by listening, patiently, carefully, for 4 full years, to the faint, ordinary sound of a planet quietly settling its own weight, the way any solid object gradually settles and shifts, almost imperceptibly, over time. Nobody who designed InSight specifically set out to detect 4.5 billion-year-old impact debris buried more than 1,000 kilometers underground. That discovery emerged, instead, from the patient, careful analysis of ordinary background seismic noise. Proof that even a mission built around comparatively modest, well-defined initial goals can end up revealing something considerably larger and considerably stranger than anyone involved originally set out to find. Picture it, one last time, before we close tonight. Somewhere on a flat, dusty, entirely unremarkable plain called Elysium Planitia, a small robot still sits, exactly where it finally went quiet, its once gleaming solar panels now the same dull reddish color as the ground stretching out endlessly around it. It has not moved, and will not ever move again. It has not spoken to Earth since December 2022, and it has already, quietly, permanently reshaped how an entire species understands the birth of rocky worlds. Not through anything dramatic, but through 4 patient years of simply, faithfully listening, somewhere far beneath that same silent, motionless lander. More than 1,000 kilometers straight down, through crust and mantle, and a layer of molten rock nobody specifically predicted in advance, sit fragments of debris considerably older than the planet's own current dusty red surface, older than any fossil ever found on Earth, older, in fact, than Earth's own moon. Survivors of a violence so overwhelming it briefly turned entire continents of solid rock into open oceans of glowing liquid magma. Sealed away, undisturbed, the moment Mars' own outer shell finally, permanently stopped moving and simply never disturbed again for 4.5 billion consecutive years. We found them not by touching them, and not by seeing them in any conventional sense of that word at all, but by listening, patiently, to the sound an entire planet makes as it quietly, continuously settles its own ancient bones. The lander's own final message, composed in the gentle, first-person voice the mission had used throughout its entire operational life, remains genuinely worth returning to, one more time, before we close tonight. My power's really low, so this may be the last image I can send. Don't worry about me, though. My time here has been both productive and serene. Productive in the most literal sense the word could ever possibly carry. A crust mapped, a mantle measured, a hidden molten layer discovered, a liquid core confirmed, a solid inner core detected, and, quietly waiting inside all of it, the actual physical fingerprint of the solar system's own violent, chaotic birth, still sitting there, patiently, exactly where it settled 4.5 billion years ago, and serene in a way that feels, somehow, genuinely fitting. A single small machine, alone on an entire empty planet, doing nothing more dramatic than listening, patiently, for 4 full years. And in doing so, hearing something no human being had ever managed to hear before, the actual, physical sound of a world remembering the precise moment of its own creation. Tonight we explored what NASA's InSight lander discovered, quietly listening to the interior of Mars for 4 patient years, and why what it eventually found, buried deep inside the planet's own mantle, genuinely shouldn't still exist at all. We found that humanity has never dug anywhere close to any planet's true interior, not our own, and certainly not Mars, and that our single deepest hole, the Kola Superdeep Borehole, reaches barely 0.2% of the way to our own planet's centre. We found that the only genuine way to see inside a planet at all is to listen to it shake, a technique painstakingly developed by a small handful of scientists working alone across 4 careful decades to fully map the interior of our own world using nothing but faint, indirect vibrations. We found a small, lonely spacecraft, delayed by a vacuum leak, launched from America's west coast for the very first time, that spent 4 years listening to an entire planet, cataloguing 1,319 separate Marsquakes, surviving a genuinely heartbreaking instrument failure, and eventually going quiet beneath its own accumulated dust, leaving behind a final message describing its own time on Mars as both productive and serene. We found a Martian interior considerably stranger than anyone fully anticipated, a crust thinner than expected, a mantle extending 1,560 kilometers deep, an entirely unpredicted molten silicate layer, a liquid metallic core, and quite possibly a solid inner core, nested at the very center of everything else. And at the heart of it all, we found kilometer-scale fragments of the solar system's own violent birth, scattered throughout that mantle in a precise, mathematically consistent fractal pattern. The exact same pattern a dropped wineglass leaves scattered across a tiled floor. Survivors of the earliest 100 million years of the entire solar system's existence, preserved not by careful design, but simply because Mars, by dying early, accidentally stopped erasing its own history the way our own living planet never has. None of this is a story about failure or about a dead, uninteresting world. It's a story about what patient listening can reveal when nothing else is capable of seeing through solid rock at all, and about the genuinely strange, humbling fact that a planet's own death may be the very thing that preserved, for us, the clearest surviving record we will ever have of how any rocky world is actually born. Sleep well tonight, knowing that somewhere above you, a small, silent, motionless machine is still sitting exactly where it finally stopped, having already, quietly, permanently changed what we understand about the birth of worlds, using nothing more than 4 patient years of listening to the ground beneath it. Good night, and rest well under a sky that holds, somewhere within it, a red and silent world still faithfully keeping the memory of its own creation.